Okay, so we were looking at muscle. We got to pretty much the end of speaking about how force is generated by muscles, right? We talked about the mechanism by which force is generated. We said that was cross-bridge cycling. And so anything that increases cross-bridge cycling automatically increases force generation. If we have more fibers or more myofibrils with more sarcomeres, that's more cross-bridge cycling and more force generation. If we have more motor neurons, right? So more neurons attached to more fibers, that will also lead to more force generation. And then that got us looking at the size principle and recruitment. So recruitment, we said, was the idea that we could call on additional fibers if there was an instance where we needed more force generated or more tension production. We can call on additional fibers. A real world example of that is trying to lift a heavy object. It's too heavy at first, but you do have the innate strength to accomplish or overcome that load. And so when you first try to lift that, you're going to probably have a few fibers contracting or a few motor units involved. And then as you really get in there and try to lift, you're going to recruit more motor units that have more fibers and can generate more force. So this is the recruitment, and the size principle component was the order in which we recruit fibers and motor units. The smallest units are recruited first. And so we described what small means. So here, small means it's a small unit in that the neuron, right, the motor neuron itself is small. The soma of that neuron is small. The axon diameter is small. The number of fibers attached, let's get that pointer going here. All right, so the number of fibers attached is small or fewer. The size of the fibers attached is also small. The type of movement associated with these smaller motor units would be more delicate, fine movements, and they would be recruited first, okay? Large units would be recruited last. So this is going to be the biggest motor units in that the soma of these neurons are bigger, the axon diameter is larger, the number of fibers attached is more, the amount of force generated here is also more, and then the size, if you'll notice, the size of the muscle fibers are really small, the size of these muscle fibers are larger. So when we say small, we mean several factors about that muscle, its function, the motor unit itself are small, the movement that it is associated with is also small, and then if you look at the bigger motor units, those are going to have bigger fibers, bigger neurons, more power instead of more delicate movements associated with them as well. Okay, and if you think about the mechanism here, this makes sense. So bigger neurons are going to be harder to depolarize. They're going to require more ionic movement to get to that threshold, right? That threshold value for depolarization. And so it's going to be harder to depolarize a larger neuron. So it's simply more efficient for the body to recruit in the order of size, just purely from an efficiency standpoint. Let's recruit smaller fibers, they're easier to depolarize, and then we can gradually increase to our biggest units, which have bigger muscles and will be harder to depolarize. All right. Looking at the schematic at the bottom here, just representing our different types of motor units. So we have X, Y, and Z. Notice the tension production in X is smaller, okay? In Y, it's sort of intermediate, and then in Z, it's much larger. And then the excitatory input, so how much excitation it takes is also smaller. So it takes less excitatory input, and when we say excitatory input, how many action potentials will it take to fully depolarize this neuron and to actually stimulate the muscle fibers that are attached? And that is going to gradually increase as the motor unit increases as well. Right. All right. Lastly, here is the velocity of shortening. This is another variable when we look at how muscles contract, especially isotonically. So just to jog our memory here, we said isotonic contractions were contractions that actually overpower the load, and so the tension levels off. So that's where we get that isotonic from. So as long as we're producing enough tension to overcome a load, that amount of tension flattens off and the tension becomes the same. So isotonic contractions, which is where the muscle shortens and the contraction levels off, can have a difference in the velocity depending on the load. So we want to think about a couple things here. When the muscle contracts, the latent period of shortening is going to increase as the load increases. What does that mean? We said the latent period is the time it takes for the machinery to warm up. So it's the time at the beginning of the twitch where the action potential has arrived, but calcium has not gotten to its place in the cytoplasm yet. And so the machinery, right, the excitation contraction coupling mechanism is happening in between the time where the action potential arrives and we begin to see force generation. So as the load gets heavier, the latent period increases, and that makes perfect sense. As the load gets heavier, the time for the machinery to warm up increases. It's going to take more time to prep, right, for excitation, contraction, coupling to get ready in order to overcome a bigger load. What else? The duration of shortening decreases as the load increases. The duration of shortening is how long that contraction is sustained. And when we say how the duration of shortening here, remember for isotonic contractions, the muscle actually shortens. How long does it stay shortened? How long does that muscle stay contracted? And how long is that contraction maintained? That time decreases as the load increases. A real world example of this is, again, lifting a heavy object. I can lift maybe a book, right, or a writing pad or a phone, and I can lift that maybe all day if I needed to. I can have that physically holding in my hand all day if I needed to, and so I could sustain that contraction for a long period of time. If I was lifting maybe a 50-pound weight or a piece of furniture or a heavy box, how long could I feasibly sustain that contraction? Much less, right? So there's a decreased duration of shortening as the load physically increases. Lastly, velocity of shortening decreases when load increases. Velocity of shortening is the speed with which the muscle shortens. So now how long it shortens for, but how fast can it actually maximally contract? That is also going to decrease as the load increases. And again, going back to our real world examples, I can lift a book pretty quickly, right off the ground, get it off the ground, get that velocity much higher very quickly, so the muscle can shorten faster. But if it were, again, a heavy object, I would not be able to begin that contraction with as much of a velocity. I would not be able to lift that as quickly. So these are the relationships that we're looking at when we talk about the shortening of the muscle and how the velocity can change as the load changes. So if we look at the graph here on the right, here's our shortening velocity. In other words, how fast the muscle contracts. Here's our load on the X. Notice the curve here. We're starting on the left here with maximum velocity, zero load. In other words, I can lift a light object very quickly. And then all the way out here, this is where the load is at the max, right, that the muscle can produce. So the maximum force that a muscle can produce is equal to the load here. And notice the heavier the load gets, the lower the velocity of shortening is. So all the way out here, very low in terms of the Y point here. So there will become a time where if I cannot physically lift the load, the velocity is zero, right? So a very light load I can lift very quickly. Intermediate load I can lift a little bit slower. A very heavy load I can lift very slowly until the velocity becomes zero because I physically cannot lift that load. All right, so it reaches zero when the load is greater than the maximum tension that the muscle will allow. Let's look at the last another curve here. This one is actually showing us the slope of the difference here, which is the velocity of the shortening. So the distance shortened here, the time that it takes for that shortening here, and notice how the curves change for different loads. So we start out in the green curve with a load that is 0. If we look at the distance shortened, that's greater. So the muscle will shorten a greater distance. In other words, it will be a greater contraction, which will mean more force. But if you look at the latent period here too, so this little beginning tells us how quickly the contraction will start. Notice that for a light load, the contraction starts immediately. All right, and then the span of the curve, right, so this entire region under here is the entire duration of that shortening. So notice for a load that is 0, I can maintain that for a longer duration. So I can power it more quickly, right, starts off right at 0. I can have a greater distance of shortening, and then I have a longer duration of shortening as well. Compare that to an intermediate load, which takes a little bit more time to warm up, shortens to a smaller or shorter distance, and then is sustained for a shorter amount of time. And then lastly, a heavy load. So a very heavy load takes even longer to get that contraction started. So notice this longer latent period here. It will generate less of a shortening, so the muscle will not physically shorten as much, and then the duration for which we can sustain that contraction is much shorter, right? So about 20 milliseconds here as compared to about 80 milliseconds for a 0 load. Okay. All right, so that is the end of looking at muscle contraction, force generation. I'm going to pause here. We're going to look at some checkpoint questions, and then we'll move on into the second part. Okay. All right. So I'm going to give you, let's do 3 minutes to work on these checkpoint questions, and then we'll discuss them at 10:03. Feel free to put a response in the chat box if you would like, or you can verbally share your response then. But I'm going to encourage you either way to write a response down in your notes and then modify that as we go through the discussion. That's really going to help your studying when you look back at this later on. Right, so let's take a few minutes to look at these questions. One more minute to go. All right, so let's take a look here. Okay, so quite a few responses here in the chat. So the first question, what is a twitch? And then how does an isometric twitch differ from an isotonic twitch? Okay, so a twitch is a muscle contraction in response to a single action potential. Perfect. All right, perfect way to phrase that. It's the muscle contracting in response to an action potential. It's a unit of contraction. And again, we can determine this on different levels. So whether it's the level of the muscle fiber, the level of the fascicle, or the level of the entire muscle. Isometric, the muscle is not shortening. Isotonic, the muscle is shortening. Also correct. So isometric, we have the same length in the muscle. Here, the tendons and the connective tissue stretch. So the length of the muscle doesn't change, and the load is never overcome. Isotonic contraction, the muscle shortens, right? The load is eventually overcome, and then the tension levels off. The size principle. So the second question, what is the size principle? So the size principle is the order in which recruitment occurs, small units first, and then larger units. Excellent. Excellent. I'm seeing some other responses here. So isometric, same length, great. So great way to associate those two types of contractions with the meaning of the terms, right? The meaning of the words. So isometric, same length. The muscle doesn't shorten, the load is never lifted. Isotonic, same tension. And the reasoning here is that when the tension is enough to overcome the load, we no longer need to increase tension production, and so the tension remains the same for the duration of that contraction. And then again, size principle, order of recruitment, excellent. Excellent point here to add as well, the difference in terms of larger units being harder to depolarize, smaller units being easier. And so the order of recruitment is really based on efficiency for the body. And then last question, what is the meaning of the term velocity of shortening? So the speed at which a muscle can contract or shorten, excellent. The rate of muscle contraction, also excellent. All right, so some great responses here in the chat. Thank you for sharing these, and they are all correct. Okay, and one of the importances of looking at the velocity of shortening is when we look at different loads, and this will have some implications when we look at different types of activities, different types of exercises when we move on to the next unit, which deals with the muscle metabolism. Okay.